The material from this video doesn't come from this chapter, but a later one, but it really does fit well with the types of reactions we've been talking about with benzene rings. There aren't any mechanisms to learn for these reactions, but there are quite a few of them, unfortunately. So all the reactions we're interested in this video involve diazonium ions. And so this is an example of a diazonium ion. We have a nitrogen-nitrogen triple bond, but then this nitrogen is connected to some other group, giving us a nitrogen with 4 bonds and no lone pairs, so this nitrogen has a positive charge. Now, when this diazonium ion is attached to a regular alkyl group, they're extremely unstable, and they decompose rapidly, and they're also explosive, so they're kind of hard to work with. Now, when the group it's attached to is a benzene ring, and therefore we have an aryl diazonium ion, they're much more stable, and they're actually very synthetically versatile. Now, the reason we inserted this material now is because it's related to the other reactions we've been studying. We know how to make this compound from benzene, right? We'd put on a nitro group and then convert it to an amino group. If I then react this amino group with sodium nitrite and HCl, I can make this aryl diazonium ion, and then there are a number of substitution reactions where I can then replace this diazonium ion with some other group. And so we're going to explore these other reactions that we can do with this diazonium ion in the rest of the video. So the first class of reactions that we can do with these diazonium ions are called Sandmeyer reactions. And so all of these reactions involve a copper salt where the anion that's combined with the copper is going to replace our diazonium ion. And so we could convert this diazonium ion into a bromide or a chloride. Of course, we know we can just do electrophilic aromatic substitution to get bromide and chloride ions. We can't use electrophilic aromatic substitution to get iodide ions, so this is a very convenient way to do that. We also hadn't seen any reactions where we could directly add a CN group to a benzene ring. So this gives us a way to get that functional group onto our benzene ring. Another thing that we can do if we have a cyano group is these compounds are easily hydrolyzed to be converted into carboxylic acids. So all I need to do is take this benzene ring with the cyano group, react it with acid and heat it up, and that will convert it into a carboxylic acid. We did learn another way to make carboxylic acids on benzene rings. This involves material from both chapters 17 and 18. From chapter 17, we saw how we could oxidize a benzene group with an alkyl group with chromic acid to convert it into a carboxylic acid. So if we had a benzene, we could slap on an alkyl group using either Friedel-Crafts alkylation or acylation, and then we could hit it with chromic acid to make a carboxylic acid, or if we can get the cyano group using a combination of going from an amine to the cyano group, then I just need an acid and heat to get a carboxylic acid. So what that would look like with this new strategy, let's say I had this compound. I have this isopropyl group, which is weakly activating and an ortho-para director. So through steric effects, we're going to add a group here. So if I hit that with a mixture of nitric acid and sulfuric acid, that'll put on an NO2. I can then convert that to NH2 using a two-step process of iron with acid. Oftentimes I'll put HCl here, then hit it with sodium hydroxide. That'll give me an NH2 group here. And then if I react that with sodium nitrite and HCl, it'll give me the diazonium ion. I can then do the substitution reaction with copper cyanide to get the cyano group, then heat that in the presence of acid, and it will give me the carboxylic acid. So we've seen a number of ways to get chlorine or bromine onto a benzene ring. We also just saw through Sandmeyer reactions how I can get iodine. We can also get fluorine-substituted benzenes by reacting this aryl diazonium ion with fluoroboric acid. That will replace the diazonium ion with fluorine. And we haven't seen many ways to get hydroxide onto a benzene ring, so these diazonium ions give us another way to accomplish that. If I take my diazonium ion and just heat it with water, that will replace the diazonium ion with OH. And so this is one of the few ways that we've learned, or maybe the only way to this point that we've learned to put an OH onto a benzene ring. Another reaction we can do with the diazonium ion, if I treat it with hypophosphorus acid, I can replace the diazonium ion with a hydrogen. Now, I'll be honest, when I first saw this, I was like, why the hell would they bother showing us this, right? Benzene is cheap. If I wanted benzene, I just go out and buy benzene. I don't need to synthesize it. But it did make sense when I read a little bit more, right? So this is useful when we want to use the amino group for its activating and directing effects, and then we want to get it back off. So for example, if I wanted to synthesize this compound, what I could do is first put on the amino group, right? So first I'll put on the nitro group, convert it to the amine. Now when I react this with Br2, I don't even need the Lewis acid because the NH2 is such a strong activating group. And then because of the directing effects and because it's so strongly activating, I'll add bromines at both ortho and para positions. And then I can use this process of converting the amine to a diazonium ion and then replacing it with a hydrogen to take that NH2 group back off, and I've got this tri-substituted benzene ring. So it's useful when I want to take advantage of the properties of the amino group, but not actually end up with the amino group on my final product. All right, so one last new reaction, and then we'll look at a couple of examples. So we can also use these diazonium salts as electrophiles in electrophilic aromatic substitution reactions. One of the keys, though, is, and maybe I should have underlined this already, this only works when I have activated aromatic rings. So I need either a moderate or, even better yet, a strongly activating group on my benzene ring in order for it to be nucleophilic enough in order to react with this guy as an electrophile. When that will happen, so when I have an activating group, a strongly activating group like a hydroxide, right, it's an ortho-para director, and because of steric hindrance, it's going to preferentially add to the para position. I actually add this diazonium ion to that para position. And this process is called azocoupling. These compounds are often used in what are called azo dyes because they're so brightly colored. The reason they're so brightly colored, I think when we first talked about conjugation, we may have mentioned the fact that when we have extended conjugated pi systems, that lowers the energy of the HOMO and the LUMO gap such that it's in the visible region, and so that makes compounds with extended pi systems very often colored, and these are no exception. They're often very brightly colored. Depending on the substituents that we put on the two benzene rings, we can change the energy gap between the HOMO and the LUMO and get different colors in that way. Okay, I want to finish up with two examples. In this first example, we want to propose a synthesis to convert this benzene ring into this di-substituted benzene. So when I'm thinking about how to make this product, the first thing that jumps out at me is this hydroxide. And in this chapter we learned, or this video, we learned our first way to add a hydroxide group to a benzene ring, and that was through taking a diazonium ion and heating that with water that would replace the diazonium ion with an OH. So to do that, first I need to put on an NO2, then convert that to an NH2, then a diazonium ion, and then I can convert it to OH. All right, so that's a lot, but I think we know how to do that. We've seen a couple examples of that in this video, at least, getting a diazonium onto this benzene ring. The other thing I want to consider is the positioning of the two groups, and so they're meta to one another. Both hydroxide and bromine are ortho-para directors, so I don't think I want to put on bromine first, because then when I put on the NO2, it's going to go here. And so when I think about all the different things that I'm transforming this group from, so I'm ending here with an OH, that's ortho-para. That would have come from an NH2 group, which is also ortho-para, but I would have started with an NO2 group, which is deactivating in a meta director. So I think what I want to do is first put on the NO2 group, then when I put on the benzene, it's going to go to the correct position, and then I can continue converting the NO2 into the OH that I want to end up with. So my first step, put on a nitro group. Now that I have a meta director, at this point I want to then put on the bromine. Okay, now that I have two groups on, I can then finish the process of converting this into an OH. So my first step is to get it into an amino group. In this section, the book has used H3O plus here. Back in the previous chapter, we were using HCl, so that's why I'm using HCl here. Then we'll hit it with NaOH. Okay, now I need to convert this into a diazonium ion. All right, and the final step is to get my diazonium ion and replace it with a hydroxide. What am I doing? I'm drawing the product on the arrow. I just need to write the reagents, and very simply, I just need to heat it in water, and that will replace the diazonium ion with the hydroxide, and that will complete our synthesis. Okay, this example goes back to the last reaction that we learned in this video, and that was the azo coupling reactions. And so in these azo coupling reactions, we're going to have two substituted benzenes. One of them is going to have this diazonium ion, and the other one needs to be an activated benzene ring. It needs to be activated so that it's nucleophilic enough that it will react with the diazonium ion, which is a nucleophile. And so in order to decide which two compounds are going to be which, right? So essentially what I'm asking is, where am I going to cut this, right? So is the diazonium ion going to go with the left-hand benzene ring, or is the diazonium ion going to go with the right-hand benzene ring? And so the one that doesn't have the diazonium ion is the one that needs to be activated. And so I need to investigate the groups on each benzene ring. So this is a moderate deactivator. So this seems to make it a bad candidate for the nucleophile. And so this is probably going to be the electrophile, or the one that has the diazonium ion. When I look at this benzene ring, I have a weak activator, but then I also have a strong activator. And if this is the nucleophile that we're going to add the diazonium ion to, because this is an ortho para director, we're going to preferentially put the diazonium ion here. And so I think this is going to be our likely candidate for the nucleophile, and this is our likely candidate for the electrophile, or the diazonium ion. So the two compounds that I would want to react in this azo coupling reaction are this diazonium ion and that nucleophile.